Now, still on the cycloaddition reactions, we're going to look at two specific important syntheses involved in this kind of reactions. Now, one of the syntheses involves an Osmium trioxide, Tetra, oxide reagent, and the other one is the use of ozone. Now, something is kind of interesting between these particular reagents in here because there are a lot of oxygens, and once you have oxygens, you either have the oxidation of your target reagent, or you have an hash system where you actually cleave bonds and also perform oxidation. Now, let's look at this first one over here. This Osmium tetraoxide, which is actually in this particular chemical formula, this actually adds two hydroxides groups in a syn to the double bond. So this positioning is more of a stereochemistry positioning where the addition is actually done in a syn conformation, and then that is added to a target double bond. Now, let's look at an example of this particular process. Now, first of all, this particular reaction, our reagent here acts as a dipole. What do I mean dipole? You remember in our previous video we talked about 1,3 dipole reagents and how they actually either behave as an electrophile or as a nucleophile. That is kind of similar, and how this particular reagent actually performs. Now, let's look at an example in here. We have a reagent which is in a trans state and is being subjected to Osmium tetraoxide. Now, this Osmium has an oxidation number of 8, and we'll see how it changes its oxidation state as it moves into future reaction steps in here. Now, what happens in here is that our chemical structure of our Osmium tetraoxide is in this form, and what happens now is that there is a 3+2 cycloaddition reaction where we have our double bond forming a single bond over here, which is a sigma bond, and our pi bond forming a sigma bond, and this pi bond forms a lone pair on this Osmium over here. So what we have as a result is the formation of this intermediate where we have our stereochemistry where this is actually in the opposite direction with respect to the other R group over there. Now, what happens next is that we add water to this particular compound, and this is actually done in an hydrated system, and the hydration actually leads to the substitution method where, while oxygen comes in here, this cleaves, and then the lone pair that is actually a negative charge on the oxygen actually picks up a proton on the hydrogen that is formed here to form on the water here that was actually bonded to the Osmium to then form a OH, and the same thing happens in here with another water coming in here, and then this oxygen actually picks up a hydrogen from the water that is actually bonded to the Osmium in here, and then you form a hydroxide here and over there. So what we have as a result is these products and that over there, which is a form of a dioxide Oh, sorry, this is meant to be R. Then if you redraw this, you actually have your redraw. We actually have the both hydroxides actually seen with respect to each other. Yeah, so we have a same product over there. So take note that this reaction is done in the presence of water, and also you need to note that there is a transformation of our oxidation state from 8 here to 6 over here. And once you transform this to that, you're thereby reducing it, and you need to reoxidize this in order for this to become an active species, which is this particular form, in order for we to actually perform the same reaction over and over again. So that's about it for this particular type of synthesis reaction using a 3+2 cycloaddition reaction. Now another one that we're going to look at is the ozone, and now we know that the addition or the cycloaddition that destroys bonds is actually in the form of ozolysis. And ozolysis actually introduces a symmetric ozone that is a 1,3 dipole as well, and this acting as a 1,3 dipole actually makes it to actually perform a 3+2 cycloaddition reaction with an alkene, and this unstable product that results is actually achieved by the oxygen bonding that is actually single bonded, and the energy is actually 140 kilojoules per mole, which is a oxygen single bond, and this is actually a very weak bond. Now let's look at how we'll be able to actually introduce our resonance in this particular case. So the resonance of ozone, as we know, is we have oxygen with a double bond over here, and in here we have a single bond. Then we have a negative charge here, we have a positive charge. Take note that since there's a lone pair over here, this lone pair forms a double bond here, and this double bond forms a lone pair over there. Now what we have is a resonance where we have this other species going in the opposite direction or going back and forth, with the positive charge still at the center, but the negative charge moves from this oxygen to the other end of the oxygen. Yeah, and if you want to generalize the structure of the resonance, you can just use this particular. We have a bracket negative, and on this oxygen we have a bracket negative. Then you can put the dot here and your dots there, which shows the flow of electrons in this particular region, which is kind of delocalized. Now let's go ahead by looking at all the reaction steps involved in this particular 1,3 dipole reaction with an alkene. So let's start off with this. We have a positive here, we have a 0 oxygen with a negative charge, and in here we have our alkene over here. Now in this case, what we have is a 1,3 dipole cycloaddition reaction, where by resonance here we actually form a sigma bond, and this pi bond forms a sigma bond here, and what we have is the formation of this particular 5-membered ring with no charge, surprisingly. And then due to the weak bond that is actually generated here and here, we have a cleavage of bond where this part actually cleaves off here, and then we have the cleavage of our bond here, and this particular lone pair actually forms a double bond over here. So as we form a double bond here, this bond cleaves off, and as we form a double bond here, this bond actually cleaves off over there. Now this actually is known as a reverse 1,3 dipole cycloaddition, and what we get is our intermediate products, which is a R plus oxygen, positively charged, and here is a negatively charged one, and we have a double bond with our R group. Now this is known as a carbonyl oxide, and this are carbonyl oxide. If you rotate this 180 degrees, which is an aldehyde, if you rotate this 180 degrees, what we have is this particular let me do it this way. Yeah, our group, the oxygen, and on this other side we have our oxygens with our R group over there, and this is negatively charged and this is positively charged. Why did I rotate this? The reason why I did it is because we want to perform our 3+2 cycloaddition reaction, and what we do in this case is that this lone pair forms a sigma bond, this our double bond, which is our pi bond, forms a sigma bond over here, and this our pi bond forms a lone pair on this oxygen over there. So what we have as a result is the formation of this subproduct or pre-product in here. Now once you're able to form this, what we usually do is that we add a OsO4 reagent, which actually does something quite interesting, which is to actually break a particular bond in such a way that we get two aldehydes in here. So what happens in here is that we introduce sulfur, methyl, and what we have is the sulfur actually forms a bond with this oxygen, and as that actually performs, this oxygen bond, which is one of the weakest bond here, cleaves off and forms a lone pair and forms a pi bond over here, and this bond actually cleaves off to form a double bond over here, and this bond cleaves off over here to form our lone pair, or reforms our lone pair over here. Now what we get as a result is the formation of two aldehydes and we have the formation of DMSO, which is a really an interesting solvent that is used in organic chemistry. I kind of use this a lot in my NMRs. It kind of makes my crystals to be more kind of unstable in its aqueous state, but that is just the backstory behind DMSO, which is this over here. And those are our two aldehydes that has been formed. So that's about it for this video. I'm sure it's kind of a long one, but I hope you're able to see the two interesting reactions, one by using Osmium tetraoxide and the other one using Ozone to actually either introduce a two hydroxide groups in the same to the double bond, or we actually destroy bonds by using ozolysis. Thanks for watching. See you on my next video, and be smart. Bye.